So my name is Andrea Ceiner. I work for a company called Eurotech. And we are in the machine-to-machine business since some decades, and we are Red Hat partners. And this gave us the opportunity to be here. We will go through these topics today. So we will see the challenges in an IoT typical business scenario. Then a quick introduction to MQTT. We will see how A-MQ and MQTT work together. Then we will see 4 use cases implemented with these technologies in different vertical business markets. And finally, we will have a conclusion on the open IoT community in Eclipse that we are participating with. And finally, there will be space for query and answers. Okay, typical business issues in an IoT scenario. Before going on, I would like to know how many of you already have programmed software in machine-to-machine or IoT? Okay, so I suppose the remaining 80% of you is more experienced in the enterprise software programming for enterprise applications. Okay, there are some differences. The two worlds are getting closer one to the other, but still there are some differences. We will highlight them. So a typical IoT or machine-to-machine business scenario. You have a sensor to connect, a temperature sensor or whatever, and you have to write your embedded application. I say embedded because the sensor must be reached and connected somehow, so the physical distance is an issue at the moment. So you have to connect to the sensor, you have to write a business logic, very simple, that could be a threshold in the temperature, and then to do an action, to perform an action. So not much difficult so far, because all you have to do is you have only one type of hardware to cope with, so few hardware functions to learn, just one serial connection, suppose, or just one protocol to study, and then you have a simple business logic, a single type of connectivity, suppose, over TCP/IP with your application, and one single business application to write. But then things get more complicated because you did a good job, and then on your desk comes more tasks in your backlog, and so that means that you have to connect a different kind of sensor. And probably this sensor is not anymore directly connected to your application, but is connected to a microcomputer that we normally call M2M gateways, which could be talking about an open hardware, a sort of Raspberry Pi or Arduino or BeagleBone. But there are industrial and rugged computers like the black box in the trains, in the cars, in buildings, in airplanes, etc., in vending machines. So you have to talk not directly with your sensor, but through a microcomputer in the middle. And the new sensor that you have to connect doesn't speak the same protocol. Suppose it's speaking Bluetooth Lite, and the other one instead is a serial protocol. So on the bottom side of the picture, you have the data producers, and you know that they are connected with your intermediate computer in different manners with different sensing networks. Then you might have more than one different kind of device in the intermediate level. We are still on the field, so with the two first layers of this picture starting bottom up, we are still on field. That means that we are in this room where we have sensors, and we have maybe on the door side a gateway, and then we have a gateway on the other side of the floor, and another gateway in the next floor and below. So we are still on field. We are not yet on a server side or on cloud or on my data center. And these gateways in the middle, they run different operating systems. The applications speaking with these sensors are different because the thresholds are different. The business logic, the embedded business logic might be different. One should be supposed to send all data retrieved by the sensor, and the other one instead to select the data to send to the cloud, not to transmit the temperature in every second, but to transmit the temperature only when there is a threshold exceeding. So complex business logic. And then between the cloud and these gateways, Also, the media could be different. You could have cellular communication with the problems of unreliable networks. You could have Ethernet, you could have satellite, you could have long range plus internet protocols, so different protocols also on that side. Another factor of complication is the fact that these gateways might be geographically dispersed. And your business applications could be not just one, because the more you work on it, the more let's say, it grows up. You have different business applications to analyze data, to filter data, to feed these data into your ERP applications, into your enterprise applications, which today are already computerizing the tasks that we do every day during our job, in our roles, in our company, like being in charge of the supply chain, the accounting, or my plant management. But now I want to turn these applications into IoT applications. That means that I need near real-time data coming directly from the sensors into these existing business applications. So the picture gets much more complicated. I go into this point-to-point unmanageable situation. And the points where this kind of communications can break down, can go down, are nearly everywhere. You have a point of failure between the sensor and the gateway, between the gateway and the cloud. Suppose the modem is not working properly in certain conditions. You could have problems at the broker side, which is the one manages the connections. Maybe when you have millions of connections, you start to enter into troubles. And then you could have problems inside the platform as a service, because normally these platforms are not simple software. They are modular. They are composed by many components like complex event processing, big data management, web applications, security and administration layers. So you have a complex platform, and things could go wrong also inside the platform. And finally, you could have problems between the API interfaces and the business applications, which are made with different technologies and with a different life cycle. So you coping traditionally with enterprise application, you already know these problems. They are quite common in the enterprise business. They are not so common in the M2M, which was closed, and now with the opening of the IP and with what is called Internet of Things are open to the integration, interoperability with all new kind of applications that until now had nothing to do with the machine-to-machine, while instead now they are hungry of being fed by real-time data. In this case, when you have a big problem, the best practice has always been to decouple, to break down the big problem in smaller problems, so to address one by one, so decoupling, normalizing, standardizing. So the first big simplification that you can do is separating the information technologies from the operational technologies. Do not mix them up. We will see why, and then integrate them, and then normalize them. So this is the standard architecture, I would say, now in a typical IoT scenario. This is not branded by us. This is the best practice. You have sensors, you have gateways, you have operational technologies in the cloud, and finally you have the information technologies and the business applications. If we see this picture from another perspective, we see that we have on one side the operational technologies, on the other side the information technologies. Inside the operational technologies we have devices, sensors, we have smart connected devices like the thermometer with a blue bullet which is transmitting via MQTT directly to the cloud, to the brokering cloud. Or we have the famous gateways concentrating and aggregating all the sensors and devices and human-machine interfaces in a specific area. These kind of computers, the gateways, today can benefit of software-defined gateways. We, for instance, created a framework based on OCGI. It's a Java framework. which is very common as a best practice in enterprise software, which was not absolutely common in the embedded space, where C, C++, and assembler are still dominating. But Java is growing up very rapidly and is the bridge between the enterprise software development and the embedded software development. So we, for instance, created the Java framework. There also is an open source distribution, and the main purpose of this framework is to have a software definition of the hardware functions and of the embedded application running that gateway. That is exactly what happened years ago when we had the virtualization and the software-defined storage, software-defined servers, and then created the possibility to have the dynamic data centers that today now we call cloud, so the cloud infrastructure. This is the consequence of virtualization. Then we have seen the networking function virtualization, which changed completely the shape of the market of the networking devices. Before we had specific ad hoc fit-for-purpose devices, a router, a switch, a firewall, and wasn't able to perform any other kind of function. Today we have the networking software-defined function. So that means that in a box I can upload the configuration of a router as well as of a firewall. So that box can play different kind of functions. And the same is happening now virtualizing sensors. And this is huge because sensors are nearly everywhere. Everywhere where informatics did not yet enter. Now you are sitting on a chair. This chair is a chair today. But suppose that we want to turn these chairs into people counters and into weigh scales. We just have to add a simple sensor, very, very cheap, and powered by battery, which will last 9 years and will transmit in real time how many people is sitting in that chair. And if I am the manufacturer of the chair, I want to learn how many people is sitting over there and how long, maybe also the way of the people sitting there. So you can turn objects into smart objects. That's all about operational technologies. But when we have to integrate operational technologies with information technologies, there are mainly two information that we have to send on both sides. On one side, we have to transmit data metrics collected from sensors to the business applications in near real time. On the other side, we have to send instructions from the business applications to an engine, to a vending machine, to devices connected to the cloud. So probably you already have heard there are very many protocols, not only this one, these are well known. They are not the only one. There is a jungle of protocols. Fortunately, open standards are helping a lot in normalizing also the protocol and standardizing the protocol jungle. But just to make a summary that I like, we have a jungle of protocols in the sensing network. We can have wired or wireless sensing networks, very short range, mid-range, long range, and these are different protocols. Very immature, growing up very rapidly. Today, nearly 30% of the networking is held by these kind of radio protocols or wide protocols which are costless. They do not cost the carrier, the communication, and the SIM, and the data over a SIM or an M2M SIM. So these are costless. That's why they're growing up very rapidly. Then you have the other kind of protocol from the field to the cloud, which is MQTT. CoAP is emerging. That's another protocol. They are still over TCP/IP. So here we have Internet of Things because we have EP as a common protocol, Internet protocol. On the other side, we don't have IoT. We have just M2M because we don't even have IP as a protocol. And then we have REST APIs, JMS, AMQP, making the bridge between the operational technologies and information technologies, particularly, and WebSockets, of course, for real-time communication. And then HTTP dominates the space of enterprise applications, web-based. So just to give some keywords that qualify operational technologies versus information technologies. In the operational technologies, we are in the space of real-time. We are in the space of low power, low footprint, few messages per connection, so millions of connections but few messages. This is the typical case of a sensor that for 24 hours and 59 minutes and 59 seconds and is in profound sleep. Deep sleep as a state. It's a real state of a device. Deep sleep. He will wake up a millisecond, transmit few kilobytes and go down and sleep again. Easy life. He lucky. But this is one of the typical scenarios in an IoT. So sensors behave differently rather than business applications. And then if we look instead at what happens in the IoT space is exactly the opposite. So we have high performance. So from the chipsets to the middleware, everyone was focused on high performance because the power was not a problem. So Intel is making very high performance chipsets. Red Hat, Oracle, and all the software vendors are focusing on high performance middlewares. High performance doesn't mean low power, means high power behind. Large footprint, enterprise service bus. You take one of the interoperability standards like HL7 in healthcare. You have a message that goes from one application to another application going through an enterprise service bus. This message is auto-inclusive, contains everything, the header, the footer, the semantics, the dictionaries, how to decode the code, which is the dictionary decoding the code. So the footprint is huge, but this is perfect for that requirement, the space of enterprise, interoperability, communication between applications, because applications are decoupled and the message must contain all information. This cannot work in an M2M space. So the other characteristics is that you typically have few connections. If you look at your ESB in a hospital or in an enterprise or in a plant, in a manufacturing plant, you will have finally dozens of applications, maybe hundreds of applications connected to your bus, exchanging a lot of messages continuously. So you have very many messages, few connections. In fact, the protocols like AMQP, which come from the enterprise space, are fit for that purpose, serving very, very many messages, very frequent, very reliable, high performance, few connections. So, looking now at the operational technologies, we have a platform called, it's a platform as a service called Everywhere Cloud. Inside that platform, there's a Red Hat middleware, which is the A-MQ MQTT broker. The platform has different building blocks. So having an IoT platform is not just a matter of having a broker. The broker must be compatible with more than one protocol. The main purpose of the broker is to make the translation from one protocol to the other and to be reliable, but mainly to serve the connectivity purposes. Then there are all the other functions and purposes that you have to take care of. So A-MQ is a very good middleware and gives us a very good broker because it is for high performance messages, so it's perfect to make the bridge between operational technologies and information technologies. It's cross-language and multi-protocol capability, so could translate from MQTT to A-MQ to JMS, etc., etc. And then is already ready for cloud. Another thing that we like very much is that it is based on OCGI. How many of you know OCGI? All of you, so I don't have to tell anything about OCGI, about its advantages and architecture. And another thing that we appreciate quite a lot is the fact that it is highly tunable. So you have in your A-MQ XML file a lot of parameters that you can tune. This is a great power, but also this is a great job to be done. Okay? It's 2 years that we are tuning A-MQ in about 60 parameters to reach the performances in the M2M IoT space that we want to reach. Otherwise, our IoT test cases are not passed. How many of you knows MQTT? So half of you, so a few words about MQTT. MQTT is not a brand new protocol. MQTT was designed by Eurotech and IBM together 15 years ago. The specification was written together, and also the Java implementation was written together. The main reason for which we wrote down this 40 pages specification of such a protocol was that IBM got a big deal, and we still are in the maintenance phase of that project, and we were a subcontractor of IBM. We are still managing 80% of oil and gas pipelines in North America, Canada, and United Kingdom, and this was the project. At that time, we and IBM already understood that IP would have become the protocol also for machine-to-machine communication. But in those times, the costs of telemetering over long distance, over telecom, over carrier, was extremely expensive, much more expensive than sending a person on the field to do the maintenance with a car, with a plane. So it was cheaper sending people rather than moving information. And the only worldwide coverage was given by the satellite, which was even more expensive. So we understood that HTTP was not the right protocol because it is query response. We will see in the next slide why. We understood that we were in the need to have a specific protocol that was using efficiently the bandwidth, because the bandwidth was extremely expensive, so it had to be low bandwidth, low power, because most of the devices are powered by battery, so must consume low battery. Two-way communication, that means the communication must be initiated always by the device for security reason. Then the session must remain always on, not like in HTTP that each time you have a new session ID. So the session ID must remain always that one. Then it must be publish subscribe, because it simplifies a lot of things. Another thing that we like very much of the protocol is the fact that you can have the hierarchical topic namespace, and this helps creating a partitioning of applications on the embedded side, which permits you to aggregate data and to create IoT meta models on the server side automatically. So to preserve one of the principles that on the edge side you must remain data agnostic. So you have, as soon as you plug a new sensor, you don't have to change your source code or whatever in the platform, neither on the edge node nor on the cloud, to enable that real-time communication from the sensor to the cloud. Okay, firewall friendly, because when you start the communication from the edge node, you are exiting a firewall from a local network, that is this sensing network here, to the cloud. So most of the firewalls by default permits you to get out, and they stop you when you want to enter from internet. So the fact that the communication is always initiated from a local network towards the public network is a matter of security, firewall friendly. SSL is already foreseen by MQTT, so you have the MQTT-S, so you have the secure socket and the authentication. And then today we have a very large ecosystem all around the MQTT. This is impressive, because this gives you the difference between MQTT and HTTP. And you see, for instance, the performances, how many messages per hour are received over a 3G communication in MQTT compared to HTTP. You have 160,000 messages versus 1,000 messages, 1,700 messages. All the rest of the figures are really impressive. And this means also saving battery and also reliability, because if you look at the message node losses, you see that MQTT by definition gives you a mechanism to assure the reliability of the message. You have quality of service inside, 0, 1, 2, and with the MQTT SN, also the -1. SN means sensing network. While instead with HTTP, you have to take care by yourself. So you have to create your code to take care of the reliability of the message. But the HTTP doesn't give you, by protocol, this kind of reliability, while instead the MQTT gives you such a stuff, and which is very important. Okay, so MQTT is okay for IoT, but is not enough. You know that You find also open source and free distribution either of brokers and of client, like Pajo, no, is a client MQTT. But beyond a pure MQTT client or server, there is a lot of stuff that you have to consider. On the device side, you have 6 things on transport service. You have to abstract the transport service, because if you want to change MQTT with CoAP, that is another protocol, you don't want to change your embedded application, which are running inside that projector. You want to decouple them. So first thing, you have to create a mechanism to abstract with Java APIs the transport from the real protocol. Then the credential and authentication management. This is not given by MQTT as a black box. You have to add this to the protocol. The provisioning. The provisioning must be managed. Provisioning means initializing that device. So the initialization from the cloud or through the cloud as an MQTT message goes into that device. Could be the firmware, could be the operating system, could be the software stack where the embedded applications are running. Data services. When that device is transmitting to the cloud, that device, suppose is transmitting via cellular communication. The cellular communication is by definition unreliable and is one of the most nightmares that all of us have when you go live with an IoT project. So the cellular goes down. This is pretty normal, that goes down. So you must manage the local cache, in-memory database, flashing on a local database, etc., etc. So something that you have to add in order that you can reconnect once the connection is always on and the cellular communication works again. You have to re-establish the publishing service and reconnect and forward the messages in the right priority and in the right order. If we consider also the fact that before we transmit the telemetry data, this telemetry data cannot go in clear as they have been received from the sensor. They must be transformed. First of all, they must be compressed, either for security and for performances. Then you have to give a data model for IoT. Otherwise, your business application finally will have a hard job to cope with this data and to process this data. So you need to give a topic and a namespace to partition the applications. For instance, in the topic hierarchical namespace that we use, we identify the customer and then the device, and then inside the device, the single embedded application. One could be temperature, the other one could be light, the other one could be whatever, okay? In this way, you can partition the application. This helps you creating a semantic data model. Then you have to manage some important events like birth and death and application certificates to recognize when a device go live for the first time or go down for the last time in its life. These are 2 very important events. Then MQTT is a publish-subscribe, doesn't have by default the request-response mechanism, so you have to define one by yourself, which is quite useful in very many business scenarios. If all that stuff is what you have to add at the device side, there are some stuff that you have to mind also on the server side. First of all, enforcing authentication. We are now all around the broker. So the broker itself doesn't give you all this stuff. You have to have a sort of broker assistant or broker plugin that you have to create to manage authentication, enforce authorization, access control list, role-based access control list, suppose, on specific topics, enforcing account policies, and tracking the session audit log. Then you have to reinforce the connectivity by tracking the device connectivity and inventing your mechanism to giving the real-time status of the connectivity. Then you have to decide what to do with the data. Either you want to store the data that you are receiving from the sensors in real time, or you want to dispatch this data towards an information technology stack which has big data database or whatever. So you have to have these mechanisms to dispatch, to switch, and they must be configurable. Finally, it's a very good practice to have a rule engine or a complex event processing that inspects data in real time when they arrive on the broker, and take actions based on rules that you have defined, possibly not in the source code. Another important thing is that you have to configure A-MQ to create a network of brokers and a cluster to give more reliability and scalability to your infrastructure in terms of toponymy, I think is the right word. And then to cope with the protocol translation, MQTT to A-MQ, JMS, etc. And then you can create your custom bundles on OCGI. What are the challenges of a middleware like A-MQ, which was made for requirements coming from the enterprise business? Well, mainly two. First of all, in the enterprise business, your middleware is mainly in an intranet. Here it is exposed to internet, and it has to cope with millions of connections. Few messages, but millions of connections, and this is something that normally is underestimated. So, exposing A-MQ and the broker to internet and to millions of connections, you have to go through some recommendations. So, protecting the broker instances. So, don't take the firewall default configuration. This is nothing more mistaken than accepting the default configuration. Go port by port, reduce the number of open ports, configure, secure the A-MQ connector that is a parameter in A-MQ XML, enforce SSL, configure the cluster. Decoupled SSL termination, that is another parameter in A-MQ XML from the broker node, so that you have an SSL proxy which just does the decoding of SSL to no SSL, and so you do not overload with useless work the broker, so the broker can cope with more connections. Another recommendation is that to respect OCGI, but all of you are aware about OCGI, so I will not spend words on it. So don't do it your way, respect the OCGI best practices, they are really useful. Remain in the space of in-memory, don't go through TCP/IP, there is a latency, sometimes this latency is not acceptable. Okay, network of brokers we already said. Also this could be very useful. So in A-MQ you have the possibility to fine-tune the checkpoints, the frequency of the checkpoints, the redo logs and the data logs size and frequency are recycled. Do it. Finally, tuning the MQTT. So decoupling threads and connections. So use shared connection for threads. Do not use the dedicated. They are too precious resources. Disable JMX. Better not to use it. Instead use the advisory support to create your monitoring system. But that is another feature provided by A-MQ. Increase the durable topic prefetch so that you can process bulk of messages and not instead one by one. Last recommendation from version 5.11 of A-MQ, you can try to use virtual topic subscriptions. You create a pool of subscribers and you can publish a message just to one of them and not to them all every time, which is useless. So, if so far we have seen how to use these good technologies that we have today, let's see how they have been placed in real business scenarios. We have used them in very many different verticals, so from cruise boats, fridges in the shopping malls, industrial chillers, HVAC systems, transportation, trains, taxi, gymnastic pools, energy metering, transportation, healthcare, military use cases, etc., even restrooms. But why such a diversity? Because operational technologies are horizontal. So the technologies that we have spoken so far are horizontal, either on the information technology side and the operational technology side. So to go vertical, what we have to do is create the embedded application that interface that sensor on one side, and on the other end of the picture create the dashboard or create the form or the business application function which is going to be encapsulated in already existing business application. You don't have to create a new business application. So let's see a typical use case. This is the use case that is active here at the booth. We have equipped some rooms with smart stereoscopic cameras. There is a software inside the cameras. As soon as you go through the exposition rooms in this floor, in the ballroom A, there are stereoscopic cameras counting people in and out. And these people count, then this information is mixed up with the social media. You can use the topic as a join key with a hashtag so that you can, in real time, count people, but also learn what are they talking about. So you have a typical example of Internet of People integrated with Internet of Things. The devices that are set up here are a gateway, stereoscopic cameras called people counter, and then there are a couple of environmental stations. They are monitoring in real time 20 different types of gas, particulate, PM2, PM5, PM10, nuclear radiations, probably, hopefully, we will not detect anything, and magnetic fields. Another use case of the same devices is running live since years in the Heathrow Airport. In this case, the company who won the tender with the airport to clean the restrooms was going to be kicked out of the deal because of the high number of claims of passengers passing through Heathrow. Heathrow is the largest airport of London. Because they were dirty, because no paper, no soap, etc., etc. So they met my colleagues in a convention like this, and they acquired these people counters. They understood the power of real-time data, and they changed the service from here to here. They're still in the business now, and they are making a good service now. They're very much appreciated by their customer. Because the data they retrieved went far beyond what they expected. So it was useful not only for them, but also for the customer. And I tell you why. Because first of all, they turned the schedule of the cleaning service. It was not anymore on schedule, it was on demand. So they turned the restroom in an intelligent restroom. And when the restroom was counting 15 males entering into the restroom, then was calling the staff, and the staff was going and bringing soap, paper, etc. Then they realized that some restrooms were unused. They brought the report to the customer, and the customer decided to turn a cost center, that is a restroom, into a profit center, that is a shop. So they closed the restroom and turned it into a shop, rented it as a shop, and so they turned it. So the power of information. The same devices are used in trains, buses, boats, to count people, to control if your profits are correct, because in the bus or train you have a certain percentage of people that do not purchase the ticket, so they just jump into the bus and then jump off. You want to know in which stops of the route this is happening, so that you can reinforce that part of the pathway of that line of bus, etc. In this case, we have equipped a company of taxis, and they are very much happy because first they were looking just to improve their revenues, but then they reinforced also the security of the drivers. They improve the revenues because they go exactly where there is people waiting for them. So the service improved, the customers waiting for a taxi are happier because there are never long queues. As soon as they arrive, a taxi immediately know the system dispatch the closest taxi drivers to the queue, and so the taxi arrives without calling it very soon. So never a long queue, never a long waiting time for passengers, and drivers are always picking up people, so they do not stand waiting for people. This is waste money for them. This is time without profits, so they increase the profit. And then they added a function with a button to be pushed to as an alarm button, and this triggers immediately a sort of rescue procedure. They know the position of the taxi, where it is. They switch on the loudspeakers so they can also listen to the talk inside the car. Completely different scenario. In this case, they wanted to monitor the refrigeration units in a grocery and to perform asset management remotely. Same devices, same information technologies integrated with operational technologies, a different business case. So MQTT is IoT ready, but what about us, programmers? Are we ready? So we mentioned Java. This is a report by RedMonk about all the programming languages and technology, and you can see Java is the top #1 over there in terms of lower time to market and investment protection. There are out there more than 9 million Java developers in the world. Most of them are like you in the enterprise space. But with the technologies that are available today, you don't have to learn about LoRa, Zigbee, Bluetooth, serial, hardware functions, wireless. You don't have to learn about that. This is a commodity for you. You have frameworks like the Cura project that we will talk about soon that simplifies. So all you have to know is Java. When you know Java, you can make your applications also in the M2M space. So there is not anymore a cultural gap, a cultural barrier. So the enterprise Java developers can be shifted to IoT projects without any problem. In 2012, Eurotech, Sierra Wireless, and IBM founded the Eclipse IoT work group. Eurotech donated the software-defined Java gateway with the name of Cura. When we founded the consortium, we were just 3 members. After 3 years, there are 23 members, more than 50 projects, more than 1.5 million lines of source code available, and this is the fastest growing Eclipse work group. This is really great. It's giving us a lot of satisfaction, and we are very happy to have done this switch from a proprietary software-based company, very jealous of its secrets. We are a hardware manufacturer, finally, to an open source approach. We are really happy. This is giving us a lot of satisfaction. This is not a definition made by me or by us. It's a quote by this guy, which is I like it very much. So if you have time, go to SlideShare and read his comments about IoT and open source. Open source is really important for IoT, plays an important role. In my opinion, much more important than proprietary software. So you have a Cura project, which is the software-defined gateway, or CGI based, inside the open IoT Stack for Java developers. It is attractive, it's going well. We have more than 1,000 downloads per month, so it's interesting. And we need you. I mean, if you want to be part of it, you are very welcome. You can join and you can contribute and you can make this magic grow up. So thank you very much.